Okay, so we were talking about limits yesterday, bless you. And this idea is important because we're going to use this when it comes to derivatives, the difference function, all that good stuff. Yes, ma'am. Who has the key for 3D? On the desk? Okay. Here you go, Pete. Here you go. There you go. Okay. And everybody seemed to be doing pretty well. The mathematical definition, I think, kind of threw some people for a loop. If f of x becomes arbitrarily close to a unique number L as x approaches c from either side, the limit of f of x as x approaches c is L. And of course, we write it in the limit notation that we are referring to. But what we're talking about is, think of a function. It doesn't matter what function it is. If it's a straight line, if it's a quadratic, if it's an exponential, choose a value of x. As I approach this specific x, the function is going to approach some corresponding value y. Now, the only way the limit exists is if, as you approach an x from both sides, okay, from both sides you approach the same corresponding y value. Okay, and I think we got through that one. Yes, sir.
So do all linear equations like have a limit, I guess?
As you approach a specific number, yes. Okay, and remember what we found on the first couple of examples was a lot of times direct substitution into the function pretty much provided me with the limit. Okay, would you like me to create another example to kind of help you out with that? No, they're good. Okay. So we finished up with this radical one right here, and the one thing that I want you to see, even if the function is not defined at a specific value, does not mean the limit doesn't exist. See, the y values still approached 2, even though we had a removable discontinuity in the graph. Okay, let's take a look at this next one right here. Estimate the limit as x approaches 1. Now, will direct substitution work for this one? Now, regardless of what happens in the numerator, if I plug the 1 into here, I'm going to be dividing by what? 0. So that direct substitution isn't going to help me. Now, we're going to go ahead and use the table in just a minute, but we want to be able to do something with the expression, maybe so we can still figure out what's going on, you know, aside from the table. The one thing I just thought of, wanted to go ahead and bring it up. When we say the limit as x approaches 1, that limit is only going to exist if we approach it from both directions, as we said, correct? Well, how do we show what direction we're approaching a value from? There you go. So if I were to say the limit as x approaches 1 plus, what direction is that from? That's from the right. Okay, so if you see a positive or a negative icon where a power should be, a positive tells you you're going to approach it from the right. A negative tells you you're going to approach that number from the left side. So the limit only exists if you approach the same number from both sides. Okay, now this one, I would recommend factoring. Do you guys remember a strategy called grouping? Okay. Well, if you're going to factor, the first thing you always want to do is pull out a what? A greatest common factor. So if you take a look at the numerator, x cubed minus x squared plus x minus 1, there's no common factor to all 4 of them, right? So grouping suggests, okay, if there's no GCF to all 4, maybe I can group these. And typically, you can go ahead and group the first 2, group the second 2 in parentheses, and then look to see in those smaller groups, do we have a GCF? Yeah, so what divides both x cubed and x squared? So I'm going to pull out an x squared. Now, what would that leave me? Okay, so x minus 1 plus, now, what's the GCF for x minus 1? Yeah, technically it would just be 1, right? I could always have a 1 in front, but for this one, because there isn't one specific value to pull out, I'm going to use that 1 to my advantage. Now, you'll notice this is a binomial expression. Okay, this represents one term because that's being multiplied. That's one product. Same thing for the other one. So now we don't have a greatest common factor. We have what's referred to as a greatest common binomial factor. So the group that repeats, I can pull it out And the GCFs that I pulled out originally, they combine to form a second group. If you'll put that in the tray, please, ma'am. So the x squared and the 1 that I pulled out, that would be x squared plus 1. Okay. So that's the factored version of the numerator. Now all of this is over x minus 1. And do you notice anything? I'm sorry? What do we notice now between the numerator and the denominator? We can cancel out those x minus 1s. Okay. Remember, if you were able to cancel out a common group factor, that told you there was a removable discontinuity. That means there was going to be a hole in this graph. Okay. So let's go ahead and see what this guy looks like. What is x squared plus 1? What kind of graph would that be? It's a parabola, right? How's he been transformed? Shifted to the left? Ooh. He's been shifted up. Now, if it were being shifted left or right, it would look like this. It would say x plus 1 squared or x minus 1 squared. See, I would be affecting the x before you apply the square, okay, the function operation. Okay, so this is a quadratic. Let me come on down here and give my shifted more room. Okay, so it's just x squared plus 1, so it's been shifted up 1. So here we go. This is x squared plus 1. This right here is going to be 1. Now, we know there's a hole here, right? I'm looking to my old pre-cal students. Where would the hole occur at? What value of x? Okay, Spencer, why do you say that? Why 1?
Because the value of 1 is what makes it
is what makes it undefined. That's exactly right. You're looking for the value of x that would still make that 0. Well, we see that's got to be 1. But now how would I find the corresponding y value that goes with that? You just plug it into whatever's left. Now, you don't want to plug it back into the groups that we canceled because we already know that's going to give me 0. Function doesn't exist there. So what is 1 squared plus 1? 2. So I know the whole has to take place at 1 comma 2. So if I come down here, okay, when x is 1, let's say this is 2 right here, I know there's that removable discontinuity. So it's a different graph, but this is what we were doing yesterday. If we take the limit as we approach 1, if I approach him from the left and I approach him from the right, well, we should be approaching some value of y that corresponds to that 1. But see, this is just one of those cases where direct substitution wasn't going to work. Now, how can we go ahead and find that limit? What were we doing yesterday? There's something we were filling in. We were filling in tables, right? If I take a look at the table that's already been created for me, okay, so the 1 value in question is 1, and you notice on the left side, we're getting closer from the left. The right side, we're getting closer from the right. In fact, over here, I would probably go ahead and say the limit as x approaches 1 from the left. While over here, I would say the limit as x approaches 1 from the right. So remember, the limit only exists if I approach the same value from both sides. Okay. So let's go ahead and fill in the table and see what we can do here. So this is going to take probably, several minutes. Okay. And, well, actually, we could probably cut it down. If I were to go ahead and plug in, say, 0.997 to every value of x I have here, I simplify and I get a decimal answer, right? Okay, everybody's with me? Would that be the exact same as if I were to just take x squared plus 1 and plug in that value? You don't think so? Now remember, we simplified this because this here actually does contain the factor x minus 1. And what did those do for us? The x minus 1's canceled. So if we're eliminating the same factor, we should still be getting the same value, right? But even if you don't want to do that, we can plug into the original problem. Let's see what we have here. It's x cubed minus x squared plus x plus 1. So let me get rid of all this here. Okay. Okay, so it was x cubed. So I'm going to go ahead and say parentheses 0.997. Oop, not 77. Why is that in brackets? Let me do this on the calculator or the keyboard. It's going to go a lot faster. Okay, so control divide, parentheses 0.997. Now that's cubed. Okay. Then it was minus squared. Is that right? Minus x squared. So minus parentheses 0.997 squared. Then we're going to have plus 0.997. And then was it plus or minus 1? Minus 1. And then minus 1 over 0.997 minus 1. Everybody okay? So if I go ahead and push enter, gives me 1.99401. So let's say 1.994. Okay, so 1.994. Okay. Let me go ahead and get my notes so this will go a little faster. You guys help me out with the other ones. Okay, if I were to plug in 0.998, what would I get? I got 1.996. Okay. What about if I plug in a 0.999? 1.998? 99. I just love doing that. It's very fun. I can tell you guys do too. Okay. Now, what we were talking about yesterday, I'm not big on spoilers, so let's start with the far end of the table and let's see what we actually approach. Because we like surprises, right? Okay. What should I get if I plug in 1.003? Okay, so I got 2.006. Perfect. What about 1.002? Okay, thank you, John. 2.004. And I'm looking for one more. 2.002 when you plug in 1.001. Yes, sir.
If you find the first two, doesn't that mean you have the whole?
If you find the first two. What do we mean? What do you mean?
You know, like 0.997, 0.998, can't you just find the difference and just add it if it's like similar?
Find the difference and add it. I'm not unsure. Oh, if you realize the pattern, oh yeah, you can do that. But see, you'd have to be able to recognize that pattern pretty quickly. I mean, you had two, and you've only got one left. So substitution or identifying the pattern. I mean, it's really, yeah.
But for doing like the 1.001 and the 1.002, you'd be able to use the pattern pretty easily because you just add 0.002.
Yeah, so if you definitely have patterns created in the values of x that you're plugging in, you should be able to see patterns in your y values as well.
But isn't that only if the limit exists?
Well, in this case here, the limit does exist even though the function isn't defined.
Well, yes.
Yeah.
Which is what I'm saying, like, if the limit doesn't exist, you wouldn't really be able to do that.
Well, you're still going to have patterns, but it is possible the limit doesn't exist. In fact, we have a problem coming up in just a minute. Okay. So let's take a look. On the left side, if we approached 1 from the left, looks like it's approaching what? 2. Well, on the right side, as we approach 1 from the right, looks like it's approaching 2. So they are approaching the same number from both directions. So I would say the limit as we approach 1 is 2. So very important. Even if the function is not defined at a specific location, the limit can still exist. Yes, sir?
Couldn't you just find the relationship between x and y and just multiply it by 2? Because that's just double.
What do you mean relationship between x and y?
Because, or the fx is double what x is for all of them.
So 1.994 is just 0.997 double?
Yeah. Sorry, I'm confusing myself.
Yeah. I never thought about it looking at it that way. I'm trying to think if there's ever a time when that wouldn't work. but the same relationship would hold for every x going to its corresponding y. So I think that would be fine.
Okay.
Yeah. Took me a second to figure out what you were talking about. Okay. All right, good. Very good. Okay, questions? Okay, let's try another one. Now this one immediately tells you, show what? Show that the limit does not exist. Consider the graph of the function f of x equals the absolute value of x over x. For positive values of x, function equals 1. For negative values of x, the function equals negative 1. So does anybody know what this graph would actually look like? How many people think they have an idea, but they're not 100% sure?
Is it just like
The one you showed us yesterday?
No, I did not show you this one yesterday.
Is it just half of the absolute value function?
Half of it. Yes, but it's not going to look like a V because of the division that we have. In fact, where's the only value of x that we're going to have a problem? Only at 0, because you can't divide by 0. So in fact, let's say we have this is positive 1, this is negative 1. That's what the graph of the function is going to look like. Because think about it, let's look at this function, the absolute value of x over x, okay, when x is greater than 0. Okay. Well, what does absolute value do? It's going to go ahead and take away the negative. So basically anything you plug in there, it's either going to remain positive or it's going to become positive, right? Because we're talking about the distance from 0 on the number line. So this top one will always give me a positive, but we're talking about a positive number. Now, because you're using the same value, anything divided by itself is 1, and two positives will give you a positive 1. So that's what this is talking about right here. For any positive value of x, I should always be getting a positive 1. But now if I were to say a negative value of x, if x is less than 0, well, regardless of the sign, the numerator is still always positive, but now the denominator is negative. So now you're dividing a value by its opposite. So that's why to the left of the origin, we have this negative 1 ray down here. Is everybody okay with that? Okay. So we can already tell, in fact, I brought it up at the end of class yesterday, this is a non-continuous function. In fact, you probably refer to this as a jump function because you jump from one value to the other, moving from one branch to the other. So let's see what happens in the table. Okay. So if I were to plug in -2 and then divided it by -2. Okay, where's my function here? Nah, that's not what I need. In fact, do you guys want to fill in that table real fast and then I will catch you up to you. What do I do with my paper? Oh, right in front of my face. Good Lord. And this is good that we're almost out of time here. I think we have one more question in this section, and then we start looking at average rates of change. So we should be able to pretty much get through the majority of this packet by tomorrow. Okay. So let's see. The absolute value of -2 over -2. -1. The absolute value of -1 over -1. The absolute value of -0.1 over -1. Okay. So it looks like on the left side, I can go ahead and say the limit as x approaches what? What are we approaching? 0. Okay. Of course, I said 0 and I put x there. 0 from the left, you would say it's what? -1. On the right side, absolute value of 2 over 2, 1. Absolute value of 1 over 1, 1. What would the 0.1 be? 1. So the limit as x approaches 0 from the right would be 1. And here's where we have a problem. Visually, we see they are not approaching the same y value as I approach the same value of x from both sides. The right side's approaching 1, the left side's approaching -1. So what we would say here is the limit does not exist.
No, I will put with the question.
Oh yeah, you can go ahead and put it there if you wanted to. That'd be fine. How are we doing with limits? Questions? Mm-hmm. How many people are going to run straight home, choose a problem out of their paper exam, and look at the mark scheme? Hey, at least I saw a few hands. What do you think? All right. Thank you very much, guys. We will continue this tomorrow. Yes, let me get